Try to remember to.
Okay, thank you. All right, so we are recording now. So the popular image of Ada Lovelace is she's that quaint um, uh, niece of Lord Byron, the poet, who used the punch cards to program a programmable loon, the Jacquard loon. But the true story is that it goes way, way, way deeper than that. She was an accomplished mathematician, a contemporary and colleague of Charles Babbage, a person who, even though the Babbage difference engine was not built to completion during Babbage's lifetime, actually worked out algorithms and methods, programs to input into a completed difference engine. She truly was the first programmer. So women, the role of women in computer science, foundational, fundamental. Uh, it is a enormous loss to the world that the role of women in computer science has decreased over time. And that's something that all of us hearing my voice can do something about. Uh, Not that as a male I'm not recommending you become a woman, but as a male you can do your part in encouraging the participation of women in computer science by not being an asshole. Okay. All right. So what you see on screen right now are women who are programming. Can you see the code?
Uh, I can see where the code may be, but I can't see what specific inputs they're making.
Well, tell me, where do you see the code? And I'm not talking about the text on the upper left-hand side.
That's obvious. I'm referring to the connection ports and dials that they're flicking up, down, and around across the board. They may have one variable is one line or row going downwards, or it is a column.
Mm-hmm. Well, almost. The code itself is expressed in the wires. What's connected to what? The dials.
I was going to say the dials are connected via wires to the connection ports.
Okay. The dials may be serving as inputs. They may be serving as selectors for some various options. However, the variables themselves are stored electronically. What is the code here is stored in the wires by what's connecting to what. Not that there's code in the wires. The operation of this computer, which is called an ENIAC, which ties into the picture of the room full of women on calculators, um, uh, and I'll explain that in a moment. The wires here are expressing the operation, telling the computer what to compute. The Let's talk about the name. This is an ENIAC. The word ENIAC, the name ENIAC, is similar to UNIVAC, EDSTAC, and a whole bunch of other early computers. Notice they all end in AC, and that was an abbreviation for automatic computer, as to differentiate from the human computers. Right, so that room full of women, those women are the computers. And these early machines end in AC because they are automatically computing. Okay? Now, let's tie in more about this picture. This is not how we use computers today. This is fundamentally different from the computers we have today, in that the computers that we have today, they store instructions the same way as they store data. In fact, instructions are data. Okay, now here in this picture, you're seeing I told you that variables, data, exists in a different form than these instructions, which exist in the connections between established by the wires. So the idea of storing instructions exactly the same way as you store data is something that this person came up with. So this is John von Neumann, and all computers that we are accustomed to are examples of von Neumann machines. So it was his idea that instructions should be stored in the same way as data. Now think about what that means. That means that you could read some numbers, some bits from a memory location. So that's where the data is. It's in some kind of memory. You could read some bits from a memory location and then have logic to decode the bits. And that's the instruction that you're supposed to execute. So on our ARM machines, we change the share. So on our ARM machines, we have a 64-bit ARM processor. Now, if I were to ask you, how big are the instructions on the ARM processor, what would you say?
Infinitesimally small.
Okay, expressed in bits.
Between 8 and 64.
Okay, can you narrow it down a little bit?
32.
Okay, and the answer is 32. Interestingly, even though it's a 64-bit computer, every single one of the instructions on an ARM processor, our ARM processors, are 32-bit instructions. Okay, now this is going to have some interesting consequences, which I'll point. I'll ask the question, but then I'm not going to answer it. We'll save it for another day. You'll have to think about it. Now, this is a byproduct, a consequence that this standardization, that all instructions are the same length, was a design choice. And the design choice is in keeping with something called an approach to designing computer CPUs, an approach called RISC, which is reduced instruction set computer. So an ARM processor is an example of a RISC design. As compared to the x86, which is a CISC design, or complex instruction set computer. So let me ask you, what do you think the length of an instruction is on the x86 family?
43.
Not exactly 43, but in fact, Thomas already said the correct answer for Intel, which is somewhere between 8 and something bigger. So on the complex instruction set, one of the reasons why it's so complex, it is complex, is because instructions have various lengths. So it depends on the instruction, how long it is, which, by the way, roughly maps to when the instruction was introduced to the processor. If you recall, or if you're aware, the 8080, the x86 is derived from the 8080, which goes back even further in time to the first microprocessor, the 4004. And son of a bitch, if today's x86 processors aren't backwards compatible back to the ones that are 30, 40 years old. So as new instructions were added, they just kept adding them and adding them and adding them. And so they had to make the instructions wider and wider and wider. Now, the logic to process variable length instructions is one manifestation of this complex instruction set computer design. Okay, now going back to ARM, every instruction is 32 bits, which means how many bytes are in 32 bits?
Four.
If you can't answer that immediately, you all fail, which is great because now I don't have to come to class. I can watch cat videos for the remainder of the term. 4, thank you, Jordan. Okay, so 32 bits is 4 bytes. Every ARM instruction is 4 bytes. Okay, now, because they are all of the same length, you'll see as we begin to look at things like jump tables, you can do math easily on addresses. Because you can count on every one of the instructions. You can do math on the addresses of instructions because every instruction is the same length. Now, I'm going to leave you with a question that I leave unanswered. You figure this out. What is the implication of having a fixed length instruction set? Think about an instruction like this one. Okay, that puts 1 into x0. Now, this instruction will be exactly 32 bits long, wide, I should say. And part of those 32 bits will be the bits for that say this is a move instruction. A small number of those bits will specify options, like this is a move into an X register, in fact, an X register, X0. So, for example, one of the options on the move is a move into which register. Okay, and then finally, there's some bits left for the literal with which to move. Well, not with which, but the literal that you are going to move, right? So given this picture, can you think of some problems?
Is this a rhetorical question, or do you want an answer?
No, it's not exactly a rhetorical question, because I do want you to think about it. It's just that we're going to move on without me answering it.
Mm-hmm.
So just to clarify, when we're like programming an assembly, the instructions are stored on the computer at some location?
Yes, instructions go into memory exactly the same way as data does. And it's easy for me to forget that you may not have seen a picture like the following before. So let me take an opportunity to draw the following picture, which you will see a gazillion times. And gazillion being the precise technical term for a lot. Okay, if this is address 0. And this is
You're
address
frozen.
really big.
Professor, you cut out.
And this memory that computing
We're losing you.
program's concept of RAM. Your program.
Professor?
Hang on. Yeah, I'm still here. Can you hear me?
Yeah, you were cutting out quite a bit.
All right. I'm going to ask my wife to get off the computer if she's watching a video or something. Okay, hold on.
This is why I say you've turned into a fax machine, because no one understands what fax machines are even used for anymore, or something else.
All right. She was not watching videos. So there's no explanation for this because I have 200 megabit service, something like that.
It's probably just Zoom being Zoom.
Yeah,
I
it
blame
could
the
be.
5G networks.
My previous professor mentioned that both Zoom and Google Meets are acting up because they're linked through Schoology. So we access it through Schoology.
All right. Well, it's possible, but I apologize on behalf of billionaires and multimillionaires, of which I am not one.
Yet.
Well, yeah. Well, it's not technically accurate what I just said, but I'll leave that to your imagination. Okay, so every process that's running, every program that's executing has this concept of RAM. And that concept begins at 0 and goes up to a really big number. It depends what that big number is. Depends on the system. And the picture that you're going to see a lot is going to look like this. And this is your code, and this goes to Jordan's question. This is your code and your globals, global variables. This is your stack. And one more line, sorry. This is your heap. And this is dragons.
You're cutting out again.
All right, tell me when I'm back.
We're now back for the moment.
Okay.
You cut out after you described the word heap.
The word heap. Okay. So you know what code is. Code is your instructions, and that's Jordan's question. You know what global variables are, and we'll see later why global variables are stored with the code. And I think you know what a heap is. Tell me what the heap is used for.
Heap is trying to remember from last class where we had to make that.
Am I allowed to answer, Professor?
Of course you can.
Oh, okay. So the heap is where you, as the programmer, intentionally allocate memory, as opposed to just the stack, which it happens automatically.
That's a wonderful answer. I couldn't have said it better myself. To add a little bit of more meat onto those bones, when we talk about allocating memory on purpose, that would be something like new and delete, deallocating, and also in the lower level, malloc and free. So doing this is something that you coded. So you are intentionally allocating some memory, and that memory is going to remain allocated until you choose to free it. So that is all going to go in the heap. Now the stack, on the other hand, is memory that's allocated incidentally by virtue of your program executing. Like, how did Cephas, how did you put it?
Cephas,
I don't know.
Okay, so
How did I put-
Cephas, yeah, you phrased it very well, so I'm giving you a compliment. So the stack grows and shrinks by virtue of you calling functions and returning from functions. So this is, if you were to say you have a function and you say int f, which that goes against all the norms of society you can imagine. When you invoke function foo, it adds space on the stack for an integer called f. And when foo returns, the space on the stack is released. So you didn't intentionally, allocate. These are just local variables. So this is where all your local variables go. Now, it turns out that the stack will grow this way, and the heap will grow this way. And what separates the heap and the stack is terra incognita, dragons, unallocated memory. And you'll notice that I've done a squiggle up at the top as well. In fact, that goes typically from address 0 to address.
could you repeat what the top squiggle is? You fax machined.
Okay, so unallocated memory is wherever you see these squiggles. Attempting to, that's where the dragons live. Now, if you attempt to poke a dragon, you die. All right? So putting it into less popular terms, more technical terms, if you attempt to access unallocated memory, it causes a fatal trap. And you're going to experience them a lot. Have you ever had a segmentation fault? Have you ever seen that?
I've had a null exception billion times.
Then you have poked. Okay, so I'm unstable again?
Thomas was unstable for a minute.
Yeah.
Yeah.
That was just Carthage internet.
Yeah. Now, Cephas, I'm sure when you said Thomas was unstable, you're not really judging him, right? I mean, you're talking about his internet connection.
We're
Yeah.
judging
I played-
Carthage's internet.
Yeah.
I play D&D. I'm pretty unstable already.
Yeah. Okay. So questions about what I have just been discussing?
So does this go back to the initial question or like that you phrased on the implication of having fixed instruction set being 32?
No, this is unrelated.
Okay. Okay, then never mind.
Okay. All right, so this discussion that we're just completing was in relation to Jordan's question about storing instructions. Now, Jordan, I'm going to ask you to go way, way, way back to a few minutes ago. Was there more to your question?
No, so just to kind of clarify, like, I mean, you kind of explained it. So basically, like when I program in like, let's say C++, it goes into the memory and says, all right, this is like, it has that stuff already on the computer?
You fax
Yeah,
machined.
you broke up.
You explained everything perfectly.
Okay. Now, given that Thomas broke apart and Jordan broke apart, then I'm reasonably convinced that Rebecca is correct, that it's something having to do with either the internet at large or Zoom.
I checked
And
on the
just
website,
as you
the internet,
About
and it says
this,
that
all instruction.
Yeah, you did the thing again. I didn't understand any of that.
Okay. Well, I am going to disconnect from my hardwire and go to my own Wi-Fi. Let's see if that's any better.
No, Professor. It has nothing to do with you. It's just Zoom being poorly
Okay.
written, among other
Yeah,
things.
apparently Zoom is having problems today, according to Jordan Ball, who says according to the internet,
Okay.
problems at Zoom.
So just keep telling me to repeat, which I can actually make several computer science lessons about that. But, so if I break up, tell me to repeat.
Will do.
Okay. So once again, instructions are stored in memory. They're stored at the low addresses in your address space. As you can see here, they're stored in addresses that are relatively close to 0. Data,
Could you repeat the past
for
3 seconds or
instance, your
so?
stack where you can access.
Could you repeat the past 4 seconds or so? You fax machined.
Okay, am I back?
yeah,
Yes, you are currently back.
Okay, so code is stored at low addresses, relatively close to address 0. And you can see data is stored everywhere else, including at your stack, which is sort of like at your roof. You know, the highest addresses that you have access to. So each instruction is 32 bits, and a number of those bits define which instruction it is. That's called the op code. Then some additional bits modify the instruction. For example, if you, I gave you the, I gave you the example of the move. Let's take a look at a different example. Add x0, x0, 1. Compare that to the instruction add x1, x0, 1. This first one adds the value 1 to x0, puts the result in x0. The second instruction is the same opcode. It's still an add, but those option bits are a little different, saying that add 1 to x0 and put the result in x1. So this would be the same. They're both add instructions, but there'd be a little difference in these bits. Then the remainder is for literals, like the one in adding 1.
Could you elaborate more on what opcode is again?
Okay, so looking at a bit pattern, bits equivalent to 7 might be move. 19 might be add. 21 might be multiply. So prior to von Neumann, an add was if you connected this cable from a hole over here to a hole over here, right? But once instructions became digital themselves, you then could tell instructions apart by the opcode. Somewhere there's hardware that says if the opcode is a 7, implement a move. If the opcode is a 19, implement an add.
So when it gets converted to binary, that'll be converted to the opcode. All right, that makes sense.
Yes, that's the binary, the opcodes and all those bits, that is machine code. Okay? All right. So any questions? We've just done a few things. We did a bit of history, and we talked about the nature of instructions. Found out on this RISC architecture that we're on, all instructions are the same length. We learned about opcodes and modifications, modifiers to the operation, operation. And then there's room for a literal.
Professor, could you go down to the add commands? You're freezing out, man.
You
Oh my.
have fax machined once more.
Yeah, serious.
Hello?
Now everybody's going out. Oh my goodness.
I think Zoom is about to die or something, because... Can you hear us, Professor?
Sometimes. I hear you now.
So
Okay.
for the add x1, x0, and 1, what would the 1 do?
This one?
Yeah, I guess. Because you're saying add x0 to x1.
No. Here, follow me here. It is a 3 operand instruction. Goes this one, we're doing an add, right? This one plus this one goes into this one.
Okay. Okay.
So this is x0 equals x0 plus 1. This one is x1 equals x0 plus 1.
Would removing the x0 and x0 equals x0 plus 1 brick the system, or would it not?
By removing, I'm not sure what you mean.
Okay, we have add x0 comma x0 comma 1. If we removed that second x0, would it brick the system?
No, it would not brick the system. It would be identical to having a syntax error in your C code.
Okay.
So it would be caught by the assembler. Okay. I think we should take a small digression and define certain terms like assembler. Okay.
Also, Caleb asked a question in the chat.
Okay, please read it to me.
In ARM v8, how wide is each part of the RISC instruction?
Well, it depends.
I was
It
wondering
depends on the
if like
opcode.
the literal is a fixed length, or because I mean obviously the whole instruction is a fixed width. but I was wondering if each part was also fixed.
The opcode part, the literal portion is variable. It depends on the opcode. Okay. Where were we? Okay, I was going to say maybe we should do a short digression and define some terms like assembler. Have you heard my, forget about it, I'll just do it. So it's possible that so far you've heard the word compiler and thought code goes in to the compiler and executable comes out. Okay, this is not accurate.
Would it be instructions go into the compiler, which then spits out code?
Well, the part that's not accurate is this part. So let me break it down. When you are working on C or C++, let's say C++, and you tell to build your application, your source code goes into the preprocessor. And what comes out is your source code changed. Or I'll put a star there. So your source goes into the preprocessor, and what comes out of the preprocessor is also your source code, but it's been changed. How has it been changed? This is actually something you should know. To answer that question, let me ask you, what does the preprocessor do?
Has it checked to see if it worked?
Doesn't
No.
it inject a bunch of like the libraries and stuff and make sure that everything is it's in the same document or file?
Okay, so a line that begins with a pound sign is not part of the language. Instead, it's intercepted by the preprocessor and is a command to the preprocessor. The one that you're most familiar with is pound include, and that's exactly what Jordan was referring to. So you might want to try this. I don't recall the command option for the compiler to limit the output to only the preprocessor. But if you had include IOStream int main return 0, okay, so that's what? 4 or 5 lines. If you were to look at the output of only the preprocessor, it will be thousands of lines. Okay? So the next step, anybody have any questions?
So the preprocessor has its own set of commands that it will do if it catches include or some of the other stuff,
Yeah.
and it counts those as commands if you look at the output.
Right. So your source goes in to the preprocessor. The preprocessor intercepts commands, lines that start with a pound sign. And if it's a valid preprocessor command, it takes some action. So include inserts, or I think Jordan used the word inject, code from another location. There are other preprocessor commands. One is called pragma. another if, another if def, another else, another would be end if, and there are more.
Are the C and C++
With include, does it inject?
Okay?
You can go, Cephas.
You know, I have to point out that this is a Carthage Zoom Perry Kowalowitz first. 3 people were talking at once, so outstanding. And they were all questions. So in the order in which I heard them, Cephas first, then Jordan, and I'm not sure, but Thomas might have talked also.
Nah, I didn't.
Are the C and C++ preprocessors the same?
They're implemented in the same program, yes. However, there are some small differences. For example, Pragma, my understanding, it doesn't exist in C.
Nice. That's it.
Jordan?
So with like, let's say include IO stream, does it inject the entire IO stream or does it only inject the stuff that's used in that code?
It injects all of it.
All of it? All right.
Right. Now, with the qualification that some of these, in particular, may discard some code and include other code. Let me give you an example, and certainly, boys and girls, we are digressing, and it's fun. I love to digress. So, for example, you might have, come on, stop it.
Also, apparently the comp org class is having Zoom problems as well, so we're not the only ones.
We are the comp org class. Are you talking to somebody else?
No, I'm just stupid. Ignore me. Also, Nathan Kapresky isn't able to get back in.
Because of password or because you can't get in at all?
Can't get in at all.
Okay. Well, fortunately, we are recording. Well, we think.
Yeah, we're still recording.
Okay, so here, Jordan, is an example of where the preprocessor would include some code, but not other. Say, for instance, you had an incompatibility between the Mac and Windows, or Windows and Linux, which there are lots. You could use these preprocessor directives to do what's known as conditional compilation. So if this symbol is known, it will include this code, and it will strike, not include, the else portion. If you're not on a Mac, then it'll do the other code and strike the Mac-dependent code. Okay?
So this actually kind of builds into the question I wanted to ask. So what other scenarios would you want to be like talking to the preprocessor besides maybe just like, hey, this is for Mac or this is for Windows?
Well, that's a great question. And we will actually explore this towards the end of the course. But it's this guy, pragma, means who knows. Pragma is completely implementation dependent. There are a few standards. For example, one you may have seen is pragma once. Have you seen that? And what does
Yeah,
it mean?
yeah. It means basically to compile usually a class file just once. So the preprocessor isn't taking the same file multiple times and doing whatever it needs
Yes.
to do.
Yes, it's because it's possible to have a loop of includes. A includes B, but B includes A. That's possible. That's reasonable. Pragma once says, if you've seen this file before, if the preprocessor has seen this file before, stop, ignore it. By the way, before Pragma existed, the way that you would do it, the same thing, in other words, in C, would be like this. Let's say this was called file9.h. I don't know. This represents all the rest of your code in file9.h. And then at the very bottom would be an NDiff. So you see how this does the same thing? The very, very, very first time the preprocessor sees the symbol file9, it's not defined. So it goes ahead and defines it and then includes the file. But if you were to try to include it a second time, excuse me, I made a mistake. If not defined,
There we are.
yeah. So if you haven't seen it before, process the file.
Oh, let me in. Wonderful.
Yay, person's back.
Great. Okay. Now, Pragma, your question, Joshua, was what else can you do with preprocessor symbols? Pragma is the Wild West. So Pragma actually will cause the preprocessor to invoke plugins, essentially. So for example, later in the course, we'll see something that looks like this. So Pragma says, hey, go do something special. In this case, go to the OMP plugin and process the code based upon those commands. If you don't have the OMP plugin, this will fail. Well, actually, it'll be ignored. All right. Questions before we get back on track? Okay. So I've done this. Now I've done this. Let's go here to this document, okay? And I'd like you all to open it up yourself. It is this one. So in the reference, the ARM, is it this one? Nope, not that one. It's the one with the pretty cover. This one? Yeah, the pretty one. Okay. So it is the one that says ARM v8-A _ instruction set architecture.
You can also find these in Schoology.
Yes.
Yeah, that's great.
Okay. So I'm going to go through I got to tell you something. ARM's documentation were written by people who were so OCD that people with OCD can't stand them. Okay, so one interesting bit is that your ARM64 processor, Arch64, actually implements 3 different instruction sets. So you can set a bit that says, don't be 64-bit, instead be 32-bit. Or you can also be a thumb. Let's see, let me go, where is that? Okay, here it is. So there are 3 different instruction sets on the modern ARM processor. So it's backwards compatible with the older 32-bit ARM and also the microcontrollers, the thumb architecture. That's just interesting. You can forget I said that now. Okay, let's talk about the registers on an ARM 64-bit machine. What you're seeing here is showing you that an X register, of which there are 31, there are 31 X registers, but that a W register is just the bottom half of the same numbered X register. So W0 is the same register as X0. It's just the bottom half. Okay?
What do you mean by bottom half?
Well, looking at the picture, you see how the X register goes from bit number 0 up to bit 63, so it's 64 bits. But the W register, the only bits that count are 0 to 31. Namely, the first half of X1 is, the first half of X0 is W0.
So if I put stuff in W0, would I be able to put stuff in X0 as well?
It would, if you were putting something as a second instruction, you'd be overriding W0. They are the same bits.
But then, so let's say I store something in W0, would I be able to access that other half by chance?
Not via W. You could via X.
Okay, so I would copy it over to X0 and then write to the rest of it.
But be aware that any writing to a W register clears the upper half. So you can't like count on finding something squirreled away in bits 32 to 63.
Okay, when you say like bottom half and upper half, is this picture's like upside down or?
He means bottom as though like as terms of value of the number.
Oh, yeah. Yeah, that makes sense. Thank you.
Yeah. So then if you had something stored in W0, could you access it using X0?
Yes.
Interesting.
Keep in mind, I'll repeat what I said though, is any write. If you modify a W register, it always clears bits 32 to 63 in the equivalent X register.
But if you were to write to that same, or to like its own, so if you're saying if you write to W1, it would erase X32 through 63. But if you write to X1, it wouldn't erase through.
Well, by
definition, X0. Yeah.
Okay. Yeah, I think you got a little tied up in your tongue there.
Yeah.
So if you write to the X register, you're writing to all 64 bits. So of course you're going to overwrite the upper half.
Oh, that makes more sense.
Yeah.
So when would this be useful? Like, what's stopping me from just always using W0 instead of, or what's stopping me from always using X0 rather than W0?
Well, that's a great question. And it's exactly this. Whoops, not that, this. Char, short, int, long. So long is the X. So if you're working on a 64-bit number, you have to use an X register. But if you're working on any of the others, these are all W's.
Related to this, I have a question.
Okay, go ahead and ask the question.
So for an instruction to the ARM computer, for the literals have to be less than 32 bits.
Okay, so I'm smiling because Cephas is still thinking about the question that I left unanswered, right? That's exactly where I wanted you to go when I was pointing out that all instructions are 32 bits long, and some of those bits you can't use for literal values. Namely, you can't use these. So there are limits to how big a constant you can have without resorting to some extra instructions. Some extra work, I should say.
So yeah, do you know what the maximum size is, or does it depend? Does that depend on the opcode?
It depends on the opcode.
That seems annoying.
Yeah. But the assembler is good enough to tell you when you violate the rules. Now,
Very kind of it.
Yeah. Now, that reminds me, we digressed here, and I didn't get back to what it means to compile something. So I'm popping the stack. Forgive me. Let me finish that. All right, we'll come back to the document. So you may think that your source goes into the compiler, and what pops out is an executable. That's the way it seems, but that's not the actual mechanism. Instead, the part we talked about so far is your source goes into the preprocessor, and what comes out is your source, but different. The next step, which is generally hidden from you, is your source, but different, goes into what is really the compiler. See, this is the quote, the compiler. So what is really the actual compiler produces assembly language.
So kind of like how do not look at the man behind the curtain kind of thing.
Yeah. Mm-hmm. So the actual C or C++ compiler produces assembly language, which is generally hidden from you. The -S will leave your assembly language files laying around. Now, then your assembly language goes into, wait for it, an assembler. And that produces object code. Now, object code is an out-of-body experience for machine code. So it is machine code, but it's not executable yet. It becomes executable in the next step. And notice what I'm doing here. There you go. Now you're finally at an executable. So a collection of object code files get linked together to produce the executable. Now,
I
you
have a
all
question.
know this step actually happens because if you've ever developed, for example, if you've ever developed a program that was, and you had more than one source code file, somehow,
Professor?
yeah.
Your Bannerman has a question for you, that being Cephas.
Okay, go ahead.
So what's it called? LLVM has like this intermediary format. Is that like something between object code and assembler?
Yeah. So things like Java Java compiles to bytecode, which is a non-machine specific intermediate form. LLVM has some type of bytecode. Ultimately, something that's executable has to run.
Okay.
Right? So if you've ever developed an application that had more than one source code file, you know what the linker does. It takes more than one object file, links it together to create the executable. We will come back to this when we talk about externs. That's a keyword in C and C++. Okay, do you have any questions about this process? This is what it means when you compile.
So how do we intercept the assembly code from like a basic C++ program or whatever?
Here, I will show you. Okay. Let's see. Okay. Okay, so here is a trivial C program, okay, right? You agree? Okay, so GCC, that's the C compiler, foo.c, and that will create an executable, a.out. But if you'd like to see the leftover assembly language, you'd say, in fact, it wouldn't that, doing the following short circuits, the C compiler, it stops after, I'm going to remove rm a.out so that you see it doesn't get recreated. So GCC dash capital S foo.c, and you notice that a.out wasn't created, but foo.s assembly language was. And let's take a look. Let's do a word count on foo.c. It is 3 lines long. Let's do a word count on foo.s. It's 20 lines long. This is the x86 assembly language. Again, it's an abortion.
I'm pretty sure less is better than more.
It depends on the context. Do you
Now
want less? Do you want less money or more money?
Yeah.
Professor understands.
Mm-hmm. Yeah.
I know.
Yeah. Okay. So dash capital S. Now, if I had done this on the ARM machine, I'm going to leave this here. I'm going off on a tangent here, but I love that. This is my ARM machine. vi foo.c. I'm going to do the same thing. And GCC dash capital S foo.c. And more foo.s. Okay, so here's the ARM code. That's the return of 0. Now compare that to the x86 code. So you see why I'm teaching ARM code.
ARM code is a lot easier to read and wrap your head around.
Correct.
Does
Why sorry.
does ARM
Rebecca?
code in general have less lines than 86 code? Or is that an overgeneralization?
That's a great question. And it's an overgeneralization, and it goes also to the heart of the difference between RISC and CISC. So part of what makes the complex instruction set computer complex is they've got instructions for everything. So often on a RISC machine, because they're simpler, it may take several instructions it may take several instructions to do what a CISC machine can do in one instruction. May. So you may think that sorry. You may think that means necessarily that RISC machines are slower, and the answer is that's not true. In fact, we just found out that like the Apple M1, which is an ARM machine, is way faster than whatever Intel has right now. Okay. So Rebecca, is an overgeneralization. Cephas, did you have a question?
Yeah, why did x86 become more or less the industry standard for most applications, despite mobile phones?
Well, it's an oversimplification on my part, but I could answer that by saying they were there first. But that is a gross oversimplification. Look at the business model between Intel, the difference in business models between ARM and Intel. Now, how many CPUs per year, guess, does ARM make?
A lot. Well, ARM
Zero.
doesn't make any because
Zero.
they make the
Zero.
standard.
Right. Right. So there's an enormous difference between ARM and Intel's business models. Intel makes chips. ARM makes designs and sells the designs.
So
By the
does that
way,
mean that ARM has the patents for all these CPUs that they make?
yes, of course. Yeah. Well, they have patents to certain aspects of their CPUs.
Also, ARM is now NVIDIA, which is weird.
Why, ARM bought NVIDIA?
No, NVIDIA bought ARM.
I hadn't heard that. Thank you for that info. Now, let's talk about the company called ARM. They are ancient. ARM, in fact, one of the most popular personal computers in the earliest days of personal computers was made by the ancestor of ARM called Acorn. And Acorn is the A in ARM. Okay, and it gets even more interesting. Acorn was a derivative of the British Broadcasting Corporation, the BBC. So anyway, trivia. Okay, holy moly, let's get back to our document. What do you say?
Nah, we can distract ourselves more.
We've got to move on. Now, where we were here, when we were looking at this page, we also drew this picture. So I would like to show you 4 different add instructions. So you may be wondering, how do I add char, or how do I add a short, right, versus the long? You notice it's kind of confusing here in that only the long is the X register, but the rest are W's. So let me show you the add of, let's say, 1 to x0, putting the result in x0. So x0, x0, 1. Again, it goes from the right to the left. So a 1 is added to x0, and the result is placed in x0. The equivalent instruction for an int is the same opcode, but it's a different register. Okay, so by replacing the X's with W's, you've gone from a 64-bit add to a 32-bit add. Now, to do a short, it would be add and that says add a half word, but you're still using the W's. And this one would be add a byte, but you're still using the W's.
So I'm just still confused on why we just don't use X for everything. Like, why would we still use the W registers if X is bigger and that extra 32 bits are going to still be allocated?
Well, the 32 bits will be allocated in the instruction, but we're talking about data too, right? You know, when you say char str equals that J is an 8-bit value. So we have these 8-bit values. We need to be able to operate on 8-bit values. Now, years ago, we had to be really, really conscious of how much memory our variables consumed. When I started, I actually did start on the 8-bit processor days, but very quickly it was the tail end of 8-bit. And the latest craze was 16-bit processors. So in those days, an int then is what would be a short today. So that's a 16-bit value. That was state of the art in when I started my first business. This confusion, by the way, you can ask yourself, well, what does an int really mean? This is why I teach people now not to use ints, but to rather to include, if you're in C++, C int types. And that gives you access to explicit definitions like int 16, no, sorry, int 16 underscore t. That is definitely a signed short. And it's definitely 16 bits on no matter what processor you use. Versus also an int 32p. That is definitely a 32-bit integer no matter where you run it. Versus an int 64t, that's definitely a long.
I don't know why I'm not understanding. So like I get with the whole memory and stuff, but like if I stored something in the first chunk, in the first register, or yeah, so W0, I store it there. It's 0 through 31. But nothing can be stored in 32 to 63 without me converting that to an X. So why don't I just instantly or initially convert it to an X?
I'm now understanding your question, and I have an answer for specifically your question. For example, let's take a look at int main, int argc, and blah, blah, blah. So here's a case where we are forced to declare something to be an int because of an existing standard. So an int, argc, is a 32-bit number, and we don't have any choice. So if we want to process it correctly, we should use a W register. But if I'm coding myself, like for instance, if you're writing your own assembly language code and you're not being forced to interoperate with ints, then go ahead, use all X's. So I think I finally understood your question.
Yeah, that makes a lot more sense. Now, would it hurt to like convert that argc into X register?
Yes, you can. There, as we get into the document, no, it would not hurt.
Okay.
As we get into the document, I'll point out there's a whole section on conversion instructions. For example, there's a specific instruction that will convert a float to an int. A specific instruction that will convert a char to a long. Okay? Okay. So 31 X registers, which also means there are 31 W registers. You don't get to use all of them, however. One of those registers is special purpose. There's a register called WZR and XZR. If you read from it, you get 0. If you write to it, it's a no-op. Nothing happens. The value is gone. Further, there are a few registers like X30, which is really special. Don't write code, general code that uses X30. Bad things will happen.
Like?
Like? Here. Let's try it. I love digressing because I love to digress. All right. So here's let's see. Let's vi test.s text. Well, that's too many. Okay. So dot text means what's about to follow is code. Okay. Dot global means that that's an instruction to the linker. It means make the following symbol public to the linker. This says make sure the next thing that you put into memory begins on an even address. Okay, you ready? So you said, what happens if you use X30? So there's my program. Okay, I'm going to compile it. I'll just use the C compiler. You can even use the C++ compiler, but that's overkill. All right, so what did I call it? Test.s? Now, I haven't tried this before, but so I'm expecting this to crash. Wait. Oh, dot/a.out.
Can you go back to the code?
Sure.
I was writing a different note, and I didn't quite get what all those things meant.
Okay, there
So
it is.
that text indicates that the following is to be considered code,
Correct.
and dot global means something.
That global means publish the symbol externally to the linker.
Publish symbol.
What symbol?
The symbol is MAIN.
Oh, so you're basically telling the linker that this is the main thing.
Right, right. So hey, let's see what happens if I remove the line, right? Okay, so I removed that line. Let's see if we can compile it all the way to an executable. Look at that. It says main is undefined. But you're saying, whoa, wait. Of course main is defined. It's there in my code. But the linker can't see it because it wasn't global.
Okay, and aligns does something about making it sure it starts on a single
An even
page or whatever.
an even address.
Why do you do that?
It's a requirement of the processor. Instructions can't be placed on odd addresses.
That makes sense because 64, all those, that everything is even. That makes sense.
Right. So hey everybody, is this beginning to gel a little bit? It sounds like it is.
Wait. I have a question.
Yeah.
So an instruction can't ever be on an odd address?
Correct.
So like, are we skipping odd addresses when we add an instruction onto memory?
Well, they're all even in length, so it's always even.
So if you start at the second register and then you add an address, since it's a 4-bit instruction, you go to the 6. You go to 6, right?
No, what you said there had like all sorts of errors.
Yeah, I realized that.
Yeah, that was so wrong in so many ways.
Oh no.
Yeah.
Here I was thinking I understood, and then they started talking.
Yeah.
Oh, no.
No. Well, you see, we all agree that every variable refers to a location in memory, right? And a location in memory has a particular address. And we learned from John von Neumann that instructions are also in memory. Therefore, every instruction has an address. So instructions can only begin at even addresses.
Okay, so that's what a line 2 does. It says instructions begin at even registers.
Correct. Okay, so this program is a technically proper and correct assembly language program. But you see that by poking X30, you crash. Okay, now if this were X0 or X7, what the hell, let's put in 7. No problems at all.
So why is that?
Because X30 is a special, very, very special register. And what is it special for? X30 is the link register. And it is critical to calling functions and returning from functions. So when you have main and you call, let's say, foo, at some point there's going to be emitted a BL to foo. So that's branch with the link register. So what's going to go on here is, so here's an instruction, and let's say this is at instruction address, that's at address N. And what's the address of the next instruction, by the way?
N+4.
Perfect. N+4, and here is the next instruction. When you say BL to foo, that is a shorthand for put N+4 into X30, put the address of foo into a special system register called the program counter. And then, actually that's it. By reloading the program counter with the address of function foo, that is the jump to foo. Now, what happens on the way back? Somewhere inside of foo, there's going to be a return. The return instruction is also a shorthand. The return says, this is BL, and the return is take X30. No, let's let me rewrite that as put. Oh, better word, copy. Okay, copy X30 to the program counter. And what's in X30? The address of the original next instruction. That's how return works. Return needs to know, where does it return to? The where it returns to is stored in X30. So don't mess with X30.
So what does PC stand for again?
Program counter.
And what is that basically?
That is a great question. So we're revealing parts of the computer as we go. So the program counter is, so here's an instruction. So the program counter is a register. It's one that you can save and load. It's one that you can load indirectly. You can load it using a branch instruction, branch with the link register, or just a branch conditional. But it points to the next instruction to be executed. So executing an instruction causes the program counter, if it's not a branch, causes the instruction program counter to be incremented by 4. To go, it is the address in memory of the next instruction to be executed.
Okay, so it's kind of it tells, so it talks about like the flow of control and stuff, like, right?
It is the flow of control.
It is the flow of control, yeah.
Right. You know, when you're in your debugger and you single step, well, in C code or C++ code, when you did that, you might be stepping over multiple assembly language instructions, but you can do the same thing in assembly language. And you can actually watch the program counter go up by 4 each time other than a branch or a return. Hey, what time is class over?
I got like 7 minutes.
I'm pretty sure it ends at 2:10 because my next class is at 2:20.
Yeah,
Yeah.
class is over.
3 minutes.
Yeah,
We're done.
look, we were having so much fun, we forgot the end of class.
I thought class ended at 2:20, so
No, the next one starts at 2:20.
I don't have any other classes after this today.
Oh, well, you're welcome to come to my Python class.
Nah.
Can
No.
I?
Yeah, of course you can. You want to?
Actually, kind of. I'm doing Python in my data science course, so.
Yeah, well, today we're learning about the if statement, so come on down.
Oh, I would love to.
All right, everybody. This was, I loved having you today. This was a lot of fun. I hope you had fun, but we're late.
Yes.
We gotta sign off.
Cheers.
Thank you.